Hello, I am Rui Okura, and this is joint work with Yukiyoshi Kameyama. I'll talk about our recent work on functional programming approach to database queries. Database is often indispensable in practical applications. In the traditional approach, we use a query language such as SQL to interact with a database management system, and a programming language to do computation. This approach causes the so-called impedance mismatch problem. This is where the language integrated query comes in. Language integrated query integrates a database query language with a programming language. A typical example is Microsoft Link. It takes the link to SQL approach, namely a query expression in a link program is translated to an SQL query, sent to the database management system, and gets the result to continue computation. Language integrated query solves the impedance mismatch problem, but we can also make use of high-level features of programming languages such as composability, abstraction, and arbitrary nesting of data structures. Implementation of language integrated query is non-trivial because of nested queries. To execute this nested query, we need to execute n+1 queries, which usually takes a huge amount of time. Cheney and others solved the problem by code generation. They formalized Cooper's program transformation rules in a typed two-level language, T-Link, and proved that any cross term of table type can be translated to a single SQL query. It is an elegant result. However, the target language covers a small subset of SQL, and it is an open problem to handle aggregation and grouping, and this is the subject of our work. Grouping in SQL is indispensable for many practically useful database queries. This is an example query with grouping. Given the students table, it computes the average GPA for each department. In this query, the group by clause specifies the key for grouping, and AVG is an aggregate function to compute the average. For this example, we get the average of GPA for each group, Math and CS. Handling grouping in the code generation approach was considered difficult. Consider this nested query, a composition of two queries Q1 and Q2. The code generation approach should be able to eliminate all nested data from this query. But we cannot transform it if both Q1 and Q2 correspond to SQL's select with grouping, because for instance maximum of average cannot be expressed by a single aggregate function. Our previous work solved this problem by decomposition. The problematic part is an aggregate function only, and other operations of grouping such as extracting data from input tables and constructing output data can be expressed by existing primitives and can be transformed. So by decomposing a grouping operator into aggregation and other parts, we can transform the query in this way. Since aggregate functions are unrelated to nested data, we can completely eliminate nested data in this way. Unfortunately, the decompose and transform approach may generate unnecessarily large and inefficient queries. The left SQL query is generated by our method, which has many subqueries. It is equivalent to the right one, which is much simpler. This is the problem we address in this work. We will explain our work by a figure. Suppose I bought futon, a Japanese mattress, and bring them to my house. This is fine. But if I bought a high quality bed like this, it is too big to go through the door. By decomposing it into small pieces, I can bring them to my house. But I cannot sleep well, because we need to assemble the pieces to build a bed by myself. This was the status of our previous work. In this work, we ask an expert to reorganize the bed nicely. Now we can sleep comfortably. Futon in the previous slide represents a query without grouping, and the bed is a query with grouping. Bringing them to the house corresponds to program transformation. The result is not in a very good form, so we reorganize the small pieces to get an improved SQL query. Reorganization of queries has two purposes, namely to reduce the size of queries and to eliminate correlated subqueries as much as possible. To express our reorganization algorithm, we introduce an intermediate representation IR as a compact form of SQL. The important primitives in IR are select and gselect. The former is SQL's select statement without grouping, and the latter with grouping. Select and gselect take several arguments such as input I, output O, and the condition for filtering C. But we omit the details. To reduce the size of queries, our reorganization provides these two rewriting rules. Here, small circle means function composition, so it eliminates one nested subquery for the composition of gselect and select or select and gselect. This is the first rewriting rule. The output O' of the inner select is substituted for the input variable y of the outer gselect. This rule is similar to beta reduction in lambda calculus, but we must be careful, since substitution in our IR may break the correspondence between grouping and aggregate function. Fortunately, we can show that the first rewriting rule is safe. Since IR terms are normal forms of program transformation, the syntax of O' is limited to simple records and cannot contain aggregate functions. We can prove the safety for the second rewriting rule. In this way, we can reduce the size of the nested queries for these patterns, and this is all we can do. Since we cannot reduce the term if both functions use grouping and aggregation. The third rewriting rule eliminates correlated subqueries. A correlated subquery is a nested subquery in which the outer select has two or more inputs. Its first input is used the second input, which is a subquery. Correlated subqueries often show rather poor performance. We can eliminate a correlated subquery by a similar rewriting as before. The details are found in our paper. This is a comprehensive example for our program transformation and reorganization. Suppose we have a term in our source language query G, which contains our grouping operator G. This term uses nested data, a record of records, so we have to transform it before executing it with database. Since this term is already in decomposed form, we can transform it to a normal form. The normal form is translated to our IR, and then we apply the reorganization algorithm, and finally get an SQL query in this form. If we don't reorganize the normal form, we obtain the left term, which has nested queries. So reorganization works well for this example. We have implemented our language query G by extending our previous implementation. Then we prepared several queries and conducted experiments and compared the query size and the execution time. We also compared the performance of our approach with Microsoft's Link. We first measured the size of generated queries with and without reorganization. The test program is this one, which is a composition of 4, G, and 4. The 4 expression in query G is select without grouping, and G does grouping and aggregation. By iterating the composition n times, we get a deeply nested query of depth n. The second and third columns are the depth in SQL without or with our reorganization. And for all queries, we can reduce the query size by a factor of 2. The last 2 columns are the execution time of the generated query. And the improvement is not so remarkable, but we still got approximately 10% improvements from the unoptimized one. Our second experiment used more practical queries in many different types, and compared the performance of our approach with Microsoft's Link. The first column shows query names. We have executed 11 queries, all of which use grouping. The second to fourth columns are the execution time of the generated SQL query for Microsoft's Link, our result without reorganization, and with reorganization in this order. The fifth column is the time for the translation from query G to SQL using our reorganization. The sixth column shows the depth of queries by reorganization. We use PostgreSQL for the backend SQL engine, and the size of input tables for all queries is 10,000. Let's look at the table more closely. We notice that the translation time in the fifth column is negligible in all cases. Looking at the second column, Link failed to execute several queries. Here, AV means query avalanche, that is, too many SQL queries were generated due to n+1 query problem we mentioned in this talk, and cannot be executed within a reasonable amount of time. NA means not available, that is, the query cannot be executed in Link since the queries have nested data structures and nested grouping. On the other hand, our query G can execute all the given queries even without reorganization in this work. Comparing our old method of this work, their execution time do not differ so much for 9 queries. But they have sharp contrast for QGetQTY and QMultiple. If we don't apply reorganization, the generated query for these cases are correlated subqueries, which needs more than 1 second to execute. Whereas the queries generated by reorganization can be run in about 15 milliseconds. We believe that these results show the usefulness of our new algorithm to the extent of our benchmark. Let me summarize this talk. In a previous work, we have addressed the open problem in the literature: how to include grouping to language-integrated query while avoiding the n+1 query problem. And when we combine with this work, we have shown that queries with grouping written in our language can be small and efficient SQL queries. The key idea is reorganizing, and we can reduce the size of generated SQL queries and eliminate correlated subqueries. And then we have been able to show the usefulness of our work through 2 experiments. However, there are still other features in SQL that need to be extended except grouping. Covering them is our future work. Thank you for your attention.